So then let me start. And please interrupt me with any questions. There are no stupid questions. And so what I would like to tell you about is my general view about statistical learning and inference, in particular with respect to what is my understanding of what this all this knowledge brings to our understanding of learning, because I guess you are interested in understanding the brain, you're interested in neuroscience. Probably you know much more than me, but this is just my personal view. Okay, so now now essentially we live in very special times because essentially since say up to 20 years ago, our world was in statistical learning was a little bit like this, like the map of the world in the 18th century. And but then now we understand that learning, statistical learning, inference is related to information theory, statistical physics, information process. So there is a lot of neuroscience, of course. Okay, so this is essentially what I was telling you about my view on what has happened since, say, the last, say, 30 years in statistical learning. Our world before, it was a little bit like this. And now we understand that statistical learning is related to a lot of different disciplines from information theory, statistical physics, etc., neuroscience, of course. So in the classical statistics world, well, this was a world where we were used to do everything with empirical risk minimization, which means maximum likelihood and the type of results that we were used to deal with are sort of laws of large numbers. So all these results have to do with the limit where the number of, you have a sample, the number of points in the sample goes to infinity. You have a given model and you want to estimate parameters, etc., or do hypothesis testing, whatever. And there are very powerful concepts that enters into this picture. So one of them is sufficient statistics. So the idea that you can compress all the information, all the relevant information of your sample into few parameters, and model complexity. I will discuss a little bit about this. And so what has happened with machine learning is that instead now we can do very complex tasks like classifying images with extremely complex machines like machine learning, which essentially defy all the understanding which we have in classical statistics. So according to classical statistics, deep neural network should not work. They should not work because they have too many parameters, they should overfit, and they should, then they are just generic models, they are black box models, so they don't know anything about what a cat or what a dog is. But in spite of this, they work remarkably well, okay? So we still don't understand a lot of how they do this, okay? So what I want to do is go a little bit through some of the background concepts in classical statistics, and then address the question that I'm interested in mostly, which is to understand what learning is about. And my argument is that in order to understand what learning is about, you need a measure of relevance. Okay, and then this measure of relevance, what I'll try to argue is that it allows you to extract information from data in the undersampling regime, which is where the data is very scarce and you don't have a clue of what the true model is. And also it gives you an idea of how you should design optimal learning machine. Okay, maybe next, tomorrow, I will discuss about this other subject, which is extracting simple model from high dimensional data, okay? So this is the plan. So interrupt me whenever you want. So essentially, my idea of classical statistics is that you have a hierarchy of different problems. So the simplest type of problem is a decision problem, is a hypothesis testing. You have two hypotheses, which corresponds to whether your data comes from a distribution P1 or it comes from a distribution P2. And you want to decide which is the best model, which is the true hypothesis, okay? So this is a decision problem. Then there is a more complex problem where you assume that your data come from a model that depends on certain parameters, and then you want to estimate these parameters, okay? And then the even more complex problem is where you have many models, each of which depends on a set of parameters, and you want to understand which of these models is the right one, okay? So let me go to hypothesis testing. So how do you deal with hypothesis testing? Well, the main intuition about this thing is the one given by the asymptotic equipartition property. So what this tells you is that if you have a sample that is drawn from a certain distribution P of S, then the most likely, with essentially probability 1, when the size of the sample is very large, then the empirical distribution of the sample is very close to the true distribution, okay? So essentially, this tells you that if you have the data, the empirical distribution of the data is at a certain distance from the true distribution, then the probability to get this data from this distribution is exponentially small. Well, essentially the rate, the coefficient in front of the exponential is the Kullback-Leibler divergence, okay? So this tells you that essentially errors are, so the error and the distances are all measured in bits, okay? And so the way to do hypothesis testing is that essentially you have two distributions, P1 and P2. This is the space of all distributions. And then the best way to solve this problem is to find the optimal way to draw the boundary between these two regions. And then depending on whether the data falls in on one side or on the other side of this boundary, then you can accept hypothesis P1 or hypothesis P2, okay? Is this clear? Okay, so...
Sorry, there's a question.
How can you find
yeah.
Oh, yeah, I missed the point. It's like the line that divides between the two hypotheses.
So I cannot hear the question, but maybe you have to repeat it.
How can you find the line that divides between, like, the boundaries between the two?
So it's very broken.
It's broken. Maybe if I talk?
I can hear you well, Ben, but I cannot hear what.
Okay, so I'll ask the question. So how do you find the boundary between the two regions? So the thin red line.
Okay. So there is a theorem which is named after Niemeyer and Pearson that tells you that essentially this line should be drawn according to the log likelihood ratio. Okay, so you take the likelihood of so given a data point, you decide whether it belongs to P1 if the likelihood of the data given P1 is larger than the likelihood of the data given P2. Okay, that's how you draw this line. So this is the line where the likelihood of the data would be equal under the two models.
Cool.
Okay.
That's clear. Cool.
Okay. Very good. So now let me go to second point. So statistical inference and parameter estimation. Okay. So there essentially you have a model which tells you what is the probability of an outcome S given a set of parameters G. Okay. And now I like to put this in this form, in this exponential form, because this is the form which we are used to in physics, but also because it's a very special form in statistics. Okay, so the problem in statistical inference is that you have your model, you have some initial idea, some initial state of knowledge of what the parameters are. This is encoded in a prior distribution over the parameters. Then you get the data, which are n independent observations about of S, okay? And then, given this, you can use Bayes rule and you can compute the posterior distribution, okay? And you can compute the likelihood, maximize the likelihood, etc., estimate the parameters, etc., etc. Okay. So one question that you may ask is how much do you learn when you do this? And one measure of this is essentially the distance, how far does the posterior distribution goes with respect to the prior when you do this inference. Okay, so and this is essentially also the mutual information between the parameters and the data. It's a measure of yes, the mutual information. And if you do the calculation, this is always in the limit when n is very large. You find that the leading term is given by m over 2 times log n, which is essentially what is called the big term, the BIC term of the Bayesian information criterion. I'll come back to this. But then you have a term that only depends on the parameters and a term that depends on the prior. Okay, all of this you can understand by the fact that when you essentially when you compute, initially you have a certain distribution of the parameters. When you estimate the parameters given the data, then the error on each of the parameters decreases by a factor 1 over square root n. Okay, because this is the precision that you get, okay, from n independent data points. So essentially you gain 1/2 log n bits of precision on each parameter, okay? And this is this term here, okay? So this second term tells you how much all these parameters depend on each other. And this object is known as the Fisher information, okay? It's a susceptibility matrix. Whereas this term, this last term tells you how surprising are the maximum likelihood parameters given your prior knowledge, okay? Now, the interesting thing is that when you take a model of this type, all the information about the parameters is contained in the expected values of these functions phi. Okay, and so this is why essentially this is why the amount of information that you learn is only equal to log n, because this is the precision that you get with which you can measure this phi in a finite sample of endpoints. Okay, so this object here is much smaller than n. So essentially, it's much smaller than the total information in the sample, and which tells you that essentially the number of informative bits in a sample are very, very few, typically, when n is very large. Now, the second thing that you learn from this formula is that you learn this many bits anyhow. You don't learn anything. I mean, there is nothing that tells you in this formula whether your model is right or not, or whether the data is complete noise or it is meaningful. Okay, and in any case, you learn these many bits. So there is no guarantee that these bits are really meaningful. Okay, so there is nothing that guarantees that these things are these bits are meaningful. So, is there a question here? You have
Oh, yeah, there's a question.
I'll show it to you first. My question is, how does the Fisher information scale use the base that they're working with?
Yeah, so the question was about how it scales with the assumption of the basis. So instead of bits, if you use the natural log, so it would just change the units, right?
Sorry, can you repeat? How does it scales with the?
Yeah, if you change from log 2 to log e.
Yes. That just that just scales by a factor here, essentially. Yes, it's so. Well, it depends on how you define the DKL. I mean, how you define the mutual information. If you define in terms of nuts, you have the natural logarithm here. If you define it in terms of bits, you have the logarithm base 2. It depends on what is the unit that you use for information.
Yeah.
Okay. Okay, very good. So now, last thing is model selection. Model selection deals with the following problem. You have a data set, and then you have a number of models. Okay, model A, model B, etc., and you would like to find out which of these models is the right one. Okay, so I mean, essentially, you just apply Bayes' rule. So you have a model. You compute what is the probability of the data given the model, which is what you get by integrating the likelihood of the data with the prior distribution over all the parameters. And then you use Bayes' rule and you get what is the probability of the models of model M given the data. And this is just given by Bayes' rule. Okay. Now, again, what you find out when you do these things, I mean, imagine that you assume that all models are equally likely a priori. Then everything depends on this object, which is called the evidence or the likelihood of the data on the model. And this object again has a form which is similar to what we have seen before. Again, the key object is the likelihood computed at the maximum, but this is penalized by these two terms, which are essentially accounting for the complexity of model M. Okay, so this tells you that the right model should not be a model that has the maximal likelihood, because this would overfit. Yeah.
Can you go back just a little bit, because the sound cut out?
Okay. Okay. So this is yeah. So what I was saying, this is I'm discussing model selection, and to do model selection, you compare different models, like the one we discussed earlier, and for each of these models, you have to compute what is called the evidence, the probability of the sample given the model, which is the integral over all the parameters of the likelihood. And then you have to use Bayes' rule, okay? And now, when you do this, the key things that count are how accurate is your model, what is the accuracy of your model, what is the likelihood of the data given the best parameters of model M, but also how complex is model M. So a model that is very complex will fit very well many data, but it will have a large complexity, many parameters, for example, and so it will have a very low. It will not be preferred. Okay. Okay. So now there are many aspects of model selection which are very complicated. First, doing this integral is very complicated, but even if you do it by saddle point, so there are two problems that you have to solve. One is maximum likelihood estimation of the parameters, and this can be complicated because it can be computationally hard. If your data is very high dimensional. And the second thing is computing this term of the model complexity is very, very difficult. So this is why it's rarely done, okay? Now this, this model complexity, you can also understand it from the point of view of minimum description length, but I don't, it's really, I mean, this complexity is really the amount of bits that you need to describe the model, okay? And, or the parameters of the model, okay? And minimum description length gives you this, a framework where you can say, make this notion very precise, okay? So, are there questions or?
Yeah, there's a question.
So, what is the like this M? How is M is measured? I mean, is it just like the number of parameters? So, like,
yeah, this is the number of parameters. Yes. This is the question. Is it?
Yes.
Yeah, that was the question. Thank you.
Yeah, so if you, so this term is proportional to the number of parameters. So this term is also, so that this term is also, say, well, it's proportional to an integral, so it's not easy to understand how, sorry, there should be a logarithm here. So, but this term also is proportional to the number of parameters, because typically the determinant is the log of the determinant is scales with the size of the matrix, and the size of the matrix is of the order of the number of parameters. Okay.
Matteo, that complexity term, is that the same as the Occam factor, or?
Yes, exactly. So it's called the Occam factor. It's called the stochastic complexity, or minimum description length complexity, or sometimes it's called it's called the minimum regret because it is the number of bits that you have to say take into account because you don't know the true parameters of your model, essentially. So this is why it's called regret. Okay. Okay. So if there are no other questions, then let me go ahead. So now there are a number of issues. So if you think about all these, all what I told you about these statistical methods, or these methods in statistical learning, and well, one could discuss other methods like even supervised learning or unsupervised learning, but so well, in all these methods, what you have is that they always assume that the number of data points that you have is very, very large compared to the dimension of the data and the number of parameters. Okay, and also it assumes that you know a lot of. In many cases, it's assumed that you know a lot on. What is the generative model? Okay. Now, this is not the typical domain where, say, biology learning operates in biology, because typically statistical inference in living systems deals with very few samples, just enough samples to, for example, to take a decision. Okay, so imagine a bacterium that have to figure out whether the concentration of antibiotics is too large or not in order to, say, escape or something like that. Then decisions have to be very, very fast. So with the minimal number of data points. Okay, even say parameter estimation, well, the size of the data that we have in, say, genomics and neuroscience, etc., is such that it does not really allow us to fit models, and actually, if we fit models, we have to regularize them very strongly. Okay, and then, well, I already told you that model selection also has its own problems, but in particular, when the data is very scarce, you imagine that the posterior distribution over models becomes very, very broad, so that even if you could do Bayesian model selection, then it will not be very informative. Okay. Okay. So and then the main issue that I want to make, and this is a little bit provocative, is that all of this does not really tell us anything about learning. Okay. So if you think about learning as, say, making sense of what data means, then in all these models, in all these approaches, you decide at the outset what does making sense means. Okay, so for example, but this is true also in unsupervised learning or supervised learning. So even when you train a neural network, you decide from the outset that you think that, say, learning means minimizing an objective function, okay, which is, or maximizing an objective function, which might be the likelihood, might be the error, or whatever, okay? So there is no, maybe our brain, okay, does all these tasks, like doing hypothesis testing, parameter estimation, model selection, etc. But all these tasks are based on the fact that there is a way of building an efficient representation of the environment on which all these things can operate, okay? And the last point is that, well, learning in living systems does much more than just generalizing well. Okay, if you think about it, say what we ask to good models in statistical learning is that they are able to reproduce the data with which they have been trained. And they are able to reproduce the test data which comes from the same distribution, and they are able to reproduce it, which is like saying that being able to reproduce the statistics of the environment. Okay, but maybe in a living system, in an intelligent system, you want to do much more than this. I mean, you want to make hypotheses on your environment. You want to say draw, for example, a connection between different domains. So you learn something and then you learn something else. Then you want to make a connection between these things, etc., etc. So all of these are, say, things that say cognitive function that are being discussed in machine learning, like meta learning, transfer learning, etc., etc. And so, say, learning has to do with having, say, an architecture that can make all these functions possible. Okay. So, so it's a good point to start before, or maybe let me just, if there are questions, just ask. Otherwise, okay.
I think we can.
Yeah.
I think it's okay. I don't see any questions.
Okay. Okay. So there is another interesting general results on learning, which is the no free lunch theorems, particularly on supervised learning and in optimization, that has been, say, proved by Volper and others. So they essentially tells you that if you have an algorithm that performs well on a certain class of problem, then it essentially, if you take another problem, then there is no guarantee that it will perform better than any other algorithm. Okay. In particular, what they show is that, say, if you take cross-validation as your algorithm for, say, choosing a model, then, well, anti-cross-validation, which is taking the models that perform worst on the test data, can outperform cross-validation with probability 1/2 on if you choose the problems from uniform distribution. Okay. So now, if you look at this result, which is a mathematical theorem, so there is nothing we can do against it. But essentially, what this tells you, and what actually also the right interpretation of these theorems is that essentially there must be a distribution of interesting problem which is not uniform. Okay, so that learning, if you want to understand learning, you have to understand what are the properties of interesting problems. Okay, because as a matter of fact, we have one algorithm, which is the brain, that works rather well, at least we think, on a broad class of different problems. Okay, but probably these are all problems which are, say, interesting problems. Okay, and for sure we know that if you draw a problem at random, then most likely it's not interesting. Okay, it's not interesting because there is nothing to know, nothing to learn about this problem, because it's essentially random. Okay, so and this is also mathematically it corresponds to the principle of maximal entropy, so it has a mathematical foundation. So the bottom line is that if you want to understand learning, then it's important, it's fundamental to have a quantitative measure that tells you when the data is interesting, when the data is relevant, and when the data is not relevant. Okay, and this essentially brings me to the key point that I want to make, that you can say, I mean, that you can appreciate by the fact that our brain figures out what is relevant and what is not. Okay, so for example, if you look at these neural recordings of say grid cells, probably you are all familiar with this data. This is data recorded. Well, not this, because this is just fake data that I wrote, but it's meant to be relative to data on the medial and entorhinal cortex that should contain information on spatial cognition. Then some of these neurons have patterns that are very space informative about the space. Some of these, instead, they are not. Okay, but in some sense, the brain, or the the neurons that listen to this, the upstream neurons, figure out which of these neuron is relevant and which one is not, on the basis of the data alone, without knowing what the spatial correlate is. Okay, so there should be a notion of relevance that is intrinsic in the data, that you can measure just from the data. Okay, and of course, well, this measure of relevance is an intrinsic measure. It's not something that is defined by some optimization, by optimizing some goal function that we decide. Okay. Okay, so maybe it's a good time to start for question. I know this is but maybe just to have a feedback on whether you understand what is the main.
Yeah, sorry, I had you on mute for a second. I didn't have you on mute. I had us on mute. But do you guys understand the problem setting that we have neural activity and you have neurons that are active, and then you have downstream neurons, and how do they know whether the other neuron's interesting or not? Like in the cocktail problem for this problem with the cocktails. Do you guys get it? Do you have any questions as to like, you think it's the right question to ask? I mean, in the space of problems, it seems like an interesting one, right? Any comments?
Nature generally doesn't like care what we say about it, so it's like neurons don't care what is interesting or not.
They could care.
I think it depends a lot on the sensory stimuli. Depends on what you're looking for.
Yeah, the comment was that it would depend a bit on the sensory stimuli. So you have sensory neurons receiving input. So I guess in terms of like retinal neurons, how informative they would appear to other neurons in the hierarchy would in part depend on how interesting the sensory information is.
Yeah,
like
yes.
If it's just
Exactly.
boring bars moving across.
No, exactly. This is the whole point. This is the whole point because essentially the one key issue is that learning, in what I'm trying to explain, learning is about making sense of data that makes sense. So there is a lot of learning, literature on learning, which deals with making sense of data that does not make any sense. Okay, and let me, say there's a lot of statistics or literature on learning which is focusing on, say, algorithmic phase transitions. That is, you take a model where there is a signal and there is a lot of noise, you mix it with a lot of noise, and then you want to recover the signal, okay? So this is what I mean, and then you study this problem in the limit where there is a lot of noise, okay? And you ask yourself, how much noise can I tolerate, okay? So this is very relevant for problems like error correcting codes or things like this. When you know a lot about how the noise is generated, okay? But it's essentially a situation where you try to make sense of data that barely makes sense, okay? In what I'm trying to discuss, and what I think is relevant for the brain, is making sense of data that makes sense. I don't know whether this is clear.
Yeah, I think so, right?
Does it make sense to everybody?
Okay.
Yeah, but good to ask questions.
There's a question in the chat.
Yes.
Yeah, there's also a question in the chat. Your relevance to spatial information, to spatial location holds uniquely within clusters of neurons, clicks, but not but not for spatial location of the cluster.
Yeah, so I didn't discuss really relevance with respect to spatial location. Actually, what I want to discuss is a notion of relevance which is independent of any features. And but maybe Simone, you can elaborate a little bit on this question.
Yeah, I think we can. We can let you speak. Let me just, yeah. Now you can. Now you should be able to talk, Simone.
Hello, can you hear me?
Yes.
If I'm not mistaken, I've heard that this type of measure is only concerned with the data which neurons encode and does not concern features of the neuron among which the spatial location. So perhaps I phrase it poorly, but my question was this irrelevance with respect to features, which scales concern if we consider neurons ensembles?
Okay. So this is a very interesting question. So at the moment, yes, what we have done with the assets and others is to look at just single neurons, so the relevance of single neurons. But essentially, the general idea is to can be applied to clusters of neurons or groups of neurons. We didn't yet do that, and of course, I mean, say when you apply this measure to single neurons, then what you can ask is what are the relevant timescales, okay, over which this neural activity is interesting or relevant, okay, and this is something that we discuss in this paper. But yeah.
Thank you.
I have a very basic question. So, is there a mechanism that a single neuron can distinguish the noise from the useful data? I mean, just like some sort of interaction, it doesn't understand is it noise or is it useful data at all?
Could you hear it, Matteo?
I barely heard that. I don't know whether the question was whether is it possible to distinguish between the noise and the signal?
Well, yeah, but the question is if a neuron can do such a calculation, can see the input from a neuron and know whether at a given time of the series of spikes is because it's provided a signal or a noise.
So is this a question or a statement? I
think it was a question. Was it a question?
Okay.
Maybe here, come and ask the question. Come, it's better. The microphone is very terrible. We're working on it.
Hi.
My question is that does this single neuron even understand that this is noise? I mean, it just receives something and responds something to it. So there is no mechanism for a single neuron to understand something that is interesting at all. So it's like it's just some input and then some output, nothing more. So
yes. So so of course, statistically, this is what neurons are expected to do. So to distinguish noise between from signal, right? And now, I don't know how they do this, okay, but we are talking about, setting up a framework where you can ask these questions in a way that does not make any assumptions on what the model is, okay? So maybe we go ahead and then we take other questions. I don't know if you want to make a break at some point.
I think we're okay.
Yeah, okay. So
we had a nice break before. Or you? I'm sorry, I spoke for everybody.
Yeah, it's fine.
Do you want the break?
No breaks.
No.
Okay. So maybe I'll go on for another, say, 25, 30 minutes. But it's good that we have questions every now and then. Okay, so now the main point that I want to make is that relevance is essentially related to frequency, to the frequency with which you see different stimuli, and this frequency with which things occur in the environment actually shapes if you want, the free energy landscape of our brain. Okay, and and actually, say the brain also uses frequency. Also, it uses frequency for memory consolidation. As you know, there is this phenomenon of replay, whereby, say, episodic memory stored in the hippocampus are replayed frequently to be stored in neocortex, and essentially the brain can tune the frequency with which these memories are stored, and so it can tune essentially the relevance, how deep will the minimum corresponding to a particular pattern be. Okay. Okay, so now the general idea of how you define very generally relevance is based on the fact that you can identify very precisely mathematically what noise is. And this has to do with maximum entropy. So a distribution of maximum entropy is a distribution which is essentially uniform over a finite number of possible outcomes. And also, if you have a distribution of maximal entropy given a certain constraint as this Gibbs-Boltzmann distribution, and so on. So you have this set of this concept, maximum entropy, that allows you to distinguish, to identify what is noise. Okay. So now, if you look at a sample, imagine that you have a sample of n observation of the same system. So I imagine that these are the states of a system or the outcome of an experiment. These are discrete points, and you think that these samples come from a model, a probabilistic model, as independent rows, because you think that each of these is an independent experiment which is done under the same conditions. Okay. And then, if you make this assumption, then you can ask yourself, how many bits do I need to describe this sample? And this is essentially the number of bits that you would need to store the sample efficiently in your computer. And essentially, you would need a number of bits per data point, which is equal to the empirical entropy. Okay. So this Ks is just the number of times that you observe outcome S. Okay. Now, some of these bits are just noise, and some of these bits instead contain information about the generative model P. How to distinguish between these two? Well, essentially, you can divide this information content into two parts. One part is just the entropy of the outcomes, which occur the same number of times. And by definition, this the probability distribution over this outcome is uniform. So the distribution of maximal entropy. So this is noise. Okay, so there is no information in the sample that can help you distinguish between these outcomes here. And then the rest is an upper bound to the amount of useful information that you can have. okay? And this is what we call relevance. So we call this H of S the resolution, because it's a measure of the compression of your data. And instead, this H of K, we call it relevance, because it essentially tells you how many bits, it's an upper bound on the number of bits that you gain on the generative model, okay? So, as you see, this is a say, rather general definition of what relevance means. And then now you can compare this to what I've been discussing on, say, parameter inference. And if you really think that this is an upper bound on the number of bits that you obtain on, that you can gain on the generative model, then this must be larger than the mutual information between any model that generates the data and the parameters, the parameters and the sample, okay? So, and if you use this formula that I derived previously, then you get an upper bound on the number of parameters that you can estimate based on a sample, okay? So the larger is the relevance, the more parameters you can estimate out of a sample, okay? And this you can also argue in other ways, but say, so the relevance tells you how rich is your sample in the sense of how many numbers you can estimate, okay? So does this make sense?
Seems so.
Okay, so maybe this is not the first time you see these things. So just if you have any question, just ask. But say the idea is that you can measure, compute these two quantities very easily. So you have a data set, you compute the frequency with which each outcome occurs. You compute the degeneracy of the multiplicity, the number of states, the number of outcomes that you see k times. And then you compute these two objects, the resolution and the relevance. And you can think that as you change the resolution, as you change the level of compression, then the relevance draws a line that goes from this point, which is essentially where each outcome is different. So you have n states S that are observed just once. So this is the maximal, say, resolution. And this is the minimal resolution, where essentially all the outcomes are just the same. You observe all the times the same outcome. In both of these two cases, the relevance is zero because you don't learn anything about the generative model. Okay. Now the idea is that the higher is the relevance for a given level of resolution, the more informative is your sample, and this allows you to say define what are the most informative samples. Okay. These are just samples that have a maximal value of the relevance given the resolution, okay? And when you solve this problem, you can solve it in many ways, but what you find out is that the solution are samples that exhibit this power law behavior of the degeneracy on the frequency, okay? So this is what is called statistical criticality, okay? So maximal informative samples generally exhibit this statistical criticality. And in particular, this exponent mu is related to the slope of this line. Okay, so to the trade-off between compression and relevance. Okay, so when you have this slope which is larger than 1, it means that when you compress 1 bit, you gain in relevance more than 1 bit. Okay, so this means that you are in a noisy regime, in the sense that you can compress further and get more information out of compression. Okay, and whereas when you go past this this point where mu is equal to 1, then you enter into the regime where your compression is lossy. I mean, you compress at the expense of potentially useful information. Okay. Now, this point where mu is equal to 1 is the point where this the power law goes down as k to the -2, and this is called zip flow. Okay, so zip flow corresponds to this optimal threshold of compression, where you have the maximally compressed, lossless representation. Okay, and this zip flow occurs, say, in many systems, like words, like distribution of antibodies in immune systems. If you look at the frequency of neural patterns in the retina, then it also follows zip flow. So the idea is that, say, zip flow in this perspective is a signature of efficient representation. Okay. So are there questions?
At the moment, I don't think there are. Anyone from the public?
I have questions.
Yes, or has a lot of questions.
Yes. Okay. These are interesting questions, sure.
Yes or no, you have to ask a question.
Okay, so I'm just wondering, the deviations from zip, okay, are there particular deviations? And I think we never thought about it that way. That you never have a perfect zip flow. So you're always, you're always like,
Can you come up?
Let me get closer to them.
He's coming.
Yes, it's better. Yes, because it's.
So I'm wondering, in the data, you never have perfect zip flow. You always have some sort of deviations from it, both in the power and in going up and down the perfect line. So I'm just wondering, is it possible to look at the zip plots and think and find in which way the code is inefficient? In the sense that, for instance, if you have deviations at the end, like when the tail of the zip, or in the middle, or somewhere in the beginning, they might be different types of deviation from optimality.
Yeah. So this is something I think we should look into. So I think the deviation, say for example in these rank plots, so the very frequent words.
Before you answer, Matteo, maybe I should ask, did others understand what I was asking? The question? Sorry? I'm just trying to see, did you understand what I was asking?
So Yasser's checking to see if the students understood his question.
Yeah.
So if it is a zip law, like perfectly like that, then according to this theory, it's an optimal representation of something. You may not know what that something is, but it is an optimal. So what I'm asking now is, when you look at the data, if this is the zip law, your data is never exactly on the zip. It's the observed one is like this, and this model, the model is like that. And you always have deviations. So my question is, what type of deviations mean what type of deviation from optimality? What type of deviation from zip means what type of, if you have deviations to the end, it might mean something else. In the beginning, it might mean something else. So I'm hoping Matteo can, in 3 minutes, discover what that means.
Oh. Yeah. So these are two different regimes. So the case where you have very frequent outcomes, and the case where you have very rare outcomes. So these are, so in this tail you have many outcomes that occur the same number of times, small times, and these are very noisy. Because they are observed, because they are rare, and these are very frequent. So I think, for example, in language, there is a discussion about this because essentially these are, say, instrumental words, essentially, like words that, like articles, etc., etc. Whereas these are content words, so words that contain some meaning, okay, that are important for the so I think in this sense deviation in this upper branch will tell you something about say the structure of the language, whereas in this lower branch will tell you something about the content of the message. I don't know whether this is clear.
That's very interesting. I mean, if that is true, you probably, what you can, do you hear me, Matteo? What one can do, if this is true, if what you're saying is true, then one can look at text from the same language, but on different topics. Let's say, you know, some piece of poetry in English, if such a thing exists. And
it exists.
Oh, that guy Shakespeare.
Yeah, he's good.
And you know, another piece, like, you know, a piece of legislation or a speech by
well, I think it's no, say, for example, if you look at say the Bible, you get a very nice zip plot. But if you look at a book of cooking recipes, then it's not a very nice zip plot.
But then you're saying that the deviations are also towards the end, not at the beginning.
Yes, now I have to check. Probably the deviation would be more at the end, in the lower part.
By doing this, you can find out whether a book is about cookies or religion.
Yeah. Yes. Yes.
Good point.
And if the beginning is the deviation from the beginning, then the author didn't know the language that they were writing about. Grammatically.
Yeah. So, okay. So can I go ahead?
Yeah.
Another thing.
So, well, this is what we did with Yasser and Ryan on studying this, using this idea of the multiscale relevance to extract information, identifying relevant neurons in a model-free manner. And as you see, well, I'm not telling you what the idea is. Maybe this would be another seminar, but essentially you use this concept of relevance and you find out that what this measure tells you is not relevant, which has a low value of this index, which we call multiscale relevance, actually does not contain any information on space, on spatial correlates, or on the direction of movement for these neurons. Whereas all the neurons that contain information on the space or on the direction of movements are those which have high relevance, okay, according to our measure. And also, we could use this idea to identify relevant positions in proteins Silvia. Again, I'm not going in any detail about this, but the idea of this measure is that you can use it, especially in the undersampling regime. Okay. And also, what we tested is that if you look now at systems that are supposed to extract efficient representation of data, and then you look at what is you sample the internal states of this system, what you find is precisely that their relevance is as high as possible, is as large as possible, and the probability distribution of the frequency with which you see the different states is essentially a power law. Okay, and this is evidence from say restricted boson machines and deep belief networks. And this is also true if you look at efficient coding, I mean, the minimum description length codes. Okay, these are all examples where you confirm that essentially efficient codes and have a maximal relevance. Okay. Now, the other part which I wanted to tell you is maybe can I go on for 10 minutes?
Yeah, we have another talk at 4:30, but
So the other thing is that I want to discuss is whether you can define the same thing for just the internal state of a learning machine. Okay, so now I'm going to look at say a learning machine, by which I mean any system that that learns from an environment, like say a deep belief network or a deep neural network. And then I want to ask, what is the probability distribution of the internal states? What are the features of this probability distribution? Because essentially, learning has to do with finding out the Hamiltonian of this system. Okay, and well, the main idea is that essentially the key variables here is the coding cost. How many bits you need to code a particular state. And this is what this E of S is. And then the resolution is just the average coding cost. Okay, the average of this E. And if you think that this S is a deterministic function of the input, then this is the mutual information between the input and the internal state. And then I define the relevance as just the entropy of the coding cost. Okay, you take the probability distribution of E, which is essentially E to the minus E by definition times the degeneracy, the number of states that have energy equal to E. And then you just do P of E log P of E and sum over all the energy levels. Okay. And the argument, the idea is that essentially optimal learning machines should be those for which the relevance, this entropy of the energy of the coding cost, is as large as possible given a certain level of the resolution. Okay, and again the argument is again the same, that essentially this is your coding cost, the number of bits, the complexity of your model. Part of this goes into noise. It's just because these are the states, the distribution over the states that have the same energy is a maximum entropy distribution. So this is just noise. And the rest is a signal. Essentially, it's informative about your, say, data. Okay, and well, the outcome of this optimization problem is that degeneracy of state should be purely exponential. And this is exactly the same statement that the distribution of a frequency should be a power law. I mean, this is statistical criticality. So this statement here tells you that essentially the energy should be linear in the entropy for this model, which means also that the susceptibility should be infinite. Okay, so this should be critical models. Okay. Now let me just tell you that essentially the idea behind this definition is that really learning machines. I mean, when you think about learning, so learning is really the inverse problem with respect to statistical mechanics. So in statistical mechanics, you have a system, you have an environment, and essentially the state of the system is given by the maximum entropy principle, because essentially what you say is that the state of the system is as independent as possible from the environment. Okay, the only thing that the system knows about the environment is just one number, which is the temperature. Okay. Whereas if you want to discuss a learning system, you want a system that is whose internal state is as dependent as possible from the environment. Okay, and so the only the most generic way in which this can happen is if you have a distribution of energy which is as broad as possible, because essentially if you have data which is noisy, or say if you have a system which is like inanimate matter, does not depend, whose internal state does not depend on the environment, then the distribution of energy is very sharply peaked on one single value. Okay, so this tells you that if you have two states which have very different energies, so this must correspond to some significant difference in the structure of the environment. Okay, because otherwise you would not observe these different energies. Okay, so in the principle of maximal energy or maximal relevance is just telling you that the distribution of energies should be as broad as possible. Okay, well, you can also have an interpretation in terms of the asymptotic equipartition function, asymptotic equipartition property, but maybe what I want to just tell you is that so the statistical mechanics of systems that optimally learn is very different from the usual statistical mechanics. Again, you have a trade-off between between compression and relevance, and also these are systems that are generically critical, that have infinite susceptibility, and also you can show a general result that essentially the relevance is a lower bound on the mutual information between the internal state, the representation of the internal state of the machine, and the features that the machine extracts from the data, whatever these features are. Okay, so this means that if you maximize the relevance, if you maximize this H of E, is equivalent to having machines that extract the maximal amount of information about the hidden features. Okay, So I think maybe there are other things I wanted to discuss, but I think maybe this is already too much. And so maybe I'll stop here. And if there are questions, maybe I'll take questions.
I didn't understand if zip flow was necessarily a property of the encoder or of the environment.
Sorry, can you repeat?
You just shout it.
I think you should get closer to the microphone.
I tried to shout. I didn't understand if zip flow was a property of the encoder or of the environment.
No, so zip flow is a property of the environment, of the data. And this is essentially also corresponds to a particular distribution of energy levels in the encoder, in the representation. And if you sample this, so if you sample the internal state of the learning machine, of the representation, then you also get the zip flow. Okay. So does this? So let's say zip flow is a property of a sample. Okay. This can be a sample of the environment, or this can be a sample of the internal state of a probabilistic model. Okay. Okay. So what I've shown is that if you look at samples of natural efficient representation, like say neural code of the retina, the immune system, or language, frequency of language, or words in language, then this exhibit zip flow. But also if you look at the internal representation of learning machines, these also, if you take a sample of these internal states, then you also see zip flow. Okay, it's the same statement. Okay, so what I mean when I say that learning is about making sense of data that makes sense, what I mean is that highly relevant data should correspond to highly relevant internal representation. Is this clear? And so zip flow characterizes highly relevant samples and highly relevant representations. Okay. So if I may, I just want to finish by saying one comment that essentially, what does this imply? This picture implies for, say, machine learning. Okay, so in machine learning, you have machines that, like a restricted Boltzmann machine, that essentially, when you train them, what we have checked is that the internal representation converges to a state of maximal relevance. Okay, so the question is, why should you design a machine that starts from a state which is not of maximal relevance? Okay, can't you just start with a machine whose internal state is already a state of maximal relevance, and only learn how this projects to the data? Okay, and indeed, I mean, this relates to the fact that when you I mean, say, this makes it possible to, say, use the same So if you think about it, when you change the data, for example, or if you want to obtain a representation with a lower resolution, then you need to retrain the whole machine, okay? And so this is very inefficient. So we don't retrain the whole brain when we want to learn something new, okay? So so the fact that you can define an absolute notion of relevance means that you can design learning machines in a way which is independent of what you want to learn, okay? And this has a lot to do with applications of machine learning to transfer learning to one-shot learning, etc., etc. Okay, but well, so I think I took too much of your time, and anyway, we are going to meet tomorrow also. So
yeah, I think we can pick up after tomorrow, right?
Maybe I'll just want to say something. Matteo, you've never done actually this. That is, design an optimal machine in this way, and then see whether it can be trained on one task and then another task in a better way, let's say, than a machine that is not optimal according to this criteria.
yes, this is the next project down the line.
Yeah.
Yes, and I think it must be so, because I mean there are machines like even these reservoir computing or these extreme learning machines where you only train the output layer. You don't train the inside weights, okay? So it must be, I mean, it must be that the internal representation is not specific of what you want to learn.
Right.
It just separates the data into frequency. Okay, this is just what this is all you want to do, essentially. I mean,
yeah,
this is what.
Quite recently, there was a lot of success in replacing transformers by heavily engineered structures by simple Fourier layers. And the results were not as good, but almost as good. And the computational costs were orders of magnitude low. And there wasn't much explanation in the paper why, but it does seem to work. I mean, it doesn't entirely.
Can you send that?
I'll track it down.
Okay.
Well, let's pick up tomorrow.
Yeah.
But before we go.
Okay. See you tomorrow.